the session. Okay, the session is being recorded now, so that will be available to you, inshallah. Okay, I'm going to start now. Few circuits are left, so we're going to see those circuits quickly, and then we'll jump to some problems, and that will be inshallah. So we stop at this point. Hydraulic motor braking system. We discussed about this completely. Let me just make it full screen mode. I hope you can see the slides. Oh, okay, okay. It was close at my end. Okay. So can you say something so that I can hear you also?
Yes, yes, I can hear you.
Okay, very good. So let's start then. Recording is being done, so inshallah you'll have the whole lecture recorded for you. Okay, let's go to the slides and let's start. So what we did last time, we stopped at this point in which we talked about the braking system of the hydraulic motor. So we continue after that. Now we have two types of circuits. One circuit is called open circuit for hydraulic motor. Open circuit is a circuit in which the oil after doing work goes back to the tank, and then the pump takes the oil again from the tank and then circulates in the circuit. It's called open circuit drive. Okay, because the oil goes back to the reservoir and then it's taken again. So it's an open circuit. Both of these figures that you can see are both open circuit. So this is the braking system, and it's open circuit because you see the oil goes to the tank. See here, and this is what we saw earlier, in which we can control the the direction and also the motor in both directions. So also it's open circuit because the oil after doing work at the hydraulic motor stage goes back to the tank. Okay, so both of these examples that we saw earlier, both are open circuit drives. So if I ask you in the exam and show you, for example, this circuit, okay, ask the open circuit or closed circuit, so you see that as soon as you to the tank, it is an open circuit. Okay, see everywhere you see it's going back to the tank or the reservoir, and then the pump takes it again from the same reservoir. So that is the open circuit. What about the closed circuit? Here you go. Closed circuit drives. So let's talk about these two. Let's talk about this simple one. So this is your variable displacement or variable displacement pump. See, this arrow is showing and telling us that it is a variable displacement pump. Okay, and this is your tank, this is your strainer or the filter, and this is something, I'll tell you what is this all about. So let's first see this whole circuit, and then I'll talk about this. What is this thing? Oh, okay. Electric motor is running the pump that goes here, comes here oil. So oil again stops here because there is not much pressure to open this the pressure the pressure release valve. Okay. This arrow at this spring shows that this is adjustable pressure setting in this type of pressure relief valve. Okay, so this you can adjust based on the pressure required in the maximum pressure allowable in the circuit. Now the oil goes, oil stops here, oil goes here, and then through this strainer or filter, it goes to the motor and then it turns motor. Simply. When it does the work, the oil goes back into the line after the hydraulic motor at, of course, low pressure. Goes here, of course, goes here, there is no way because it's closed already. It comes here and it comes here. Now, when it comes here, see the pump is continuously working. So as soon as the oil comes here, the pump just pulls the oil back into the circuit, and then this oil keeps on circulating like this. Okay, so when the whole circuit is full of oil, the pump will not take any oil from here, from the tank. Okay, it will just take the oil and inside this whole circuit more oil from the tank. So once it's filled, so it will just continue to circulate this hydraulic fluid or oil in this whole circuit. Okay, so but what about not this one? If, of course, it will take the oil from the tank and then it will circulate. But what happens during the whole operation? After some time, there might be some leakages developed in the whole circuit. There might be some sort of uh, leakages or some sort of recesses produced in the pipelines or maybe in the pump oil circuit is taken by the pump that amount which is lost from this. Of course, this is again the same. Okay, don't worry. This is not different. These are the same tanks, one and two. These are one tank. Just again, as I mentioned, that they show it two times or three times or four times so that it doesn't become required to replenish the amount of oil lost in the leakage. Okay, and then continue circulating the oil. So it is a closed circuit. Simple example of this closed circuit hydraulic power system. Now this one is a little bit more complicated, but of course it is again a closed system, a closed circuit system in which you see that the oil is just being circulated and it doesn't go back to the tank. So let's try to see the whole functioning, and then we see if there is any leakage, and that leakage is covered by what means. So this is your motor that is running the pump, which is a variable displacement pump, and then this is this line which is is placed here as to replenish the lost oil. Okay, but we'll see if we need more oil, we can use this pump extra. But let's see first of all the functioning, and then we see how we can incorporate this replenishing pump into the whole circuit. Now, the both arrows in both directions mean that it is also a reversible pump, which can be run in this direction as well as the other. Okay, and it's also variable displacement, reversible hydraulic pump. So it's reversible pumps. First cycle, which is taken as the oil being pumped by the hydraulic pump in this direction. So it goes up, goes here, comes here again. Check valve, no problem. Everything is closed, so oil will not go here. Oil will go here. Again, to try to go through this one. Okay, again it's closed and the pressure is not enough to open this pressure relief valve, so nothing would happen. Even it's not pressure relief valve because this is something because it is not giving off the oil in the tank, but it is just to go through this one so that the motor can be saved. So it means that if the pressure is excessive, this will open and the oil will not go to the motor and will save the motor. Okay, the oil will just continue circulating like this. So it is closed, it is closed, the oil goes further, come here again, it is closed, goes here, does the work through the in the hydraulic motor, and then if there is any leakage, that can be seen here as this one. So if there is some leakage, you can just see some sort of a very small replenishing of the lost oil can be done in this hydraulic motor. And this hydraulic motor again, it's a reversible. See these two arrows and these two arrows. You see the difference. So please remember this thing because I can ask you the symbol of if I put this one in the final exam, you should know that this is a reversible variable displacement hydraulic pump. This is reversible hydraulic motor. Okay, so just see the arrows, how the arrows are arranged. Okay, so fixed displacement because there is no arrow, so fixed displacement hydraulic motor, but it is reversible as well. So the oil does work and then goes through this comes to the line again at a low pressure, of course, comes here again, it's closed, no way, it comes here again, closed. It will continue the pump, and the pump will continue to circulate this oil until until required. Okay, and then when it's closed, then the oil, wherever the oil is, will just stop inside the whole circuit. If the pump is turned in the opposite direction, so that oil goes, instead of up, it goes down. Okay, in that case the oil will come here. Okay, closed, no way, just stop. The remaining part of the oil would come here again, closed, then closed, comes here, moves the hydraulic motor in the opposite direction, then out into the line at lower pressure, comes here, closed, 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 and then comes back here and continues circulating in this. So in this case, so we see that these two check valves and this line is not being used, right? In the regular and normal operation, this whole line is not used because the oil comes here, there is nothing, or just go there, circulate, and does the work. And even this one. So these two are overload relief valve. See the point, overload. Why? This is what I said. If by any means the motor is stuck, or the load is more than the capacity of this motor, so it means the motor will not run and the pressure would keep on developing because the pump is continuously pushing the oil into the circuit. So in that case, this will open, and instead of going to the motor and damaging it, it will just continue going like this, like this, or in the opposite direction it will go like this. So it will not go to the hydraulic motor, and it will not damage the hydraulic motor or the amount of or the work done, which is here, or the load or something which needs to be turned or something to be moved will not be damaged. So these two bypass lines are just to save the hydraulic motor and also the work, and just keep the oil circulating in the circuit like this, without going to the hydraulic motor. Okay, so let's see this one now. So now we have to understand this whole mechanism. What is this? As I mentioned, it is closed circuit, so it means the oil will continue flowing and going in this circuit like this, opposite this outer one, the outer pipeline. Okay, so but again, as we know that the pipeline has some length, there are some joints, there are some elbows, there are some other bends and all these stuffs, all these attachments. So in those attachments, there is a possibility at high pressure those attachments after some time can start leaking. Okay, so some oil will just spill out, maybe sometimes small quantity, sometimes large quantity, but at least there will be some sort of a leakage. And because the circuit is complicated, it can have a leakage anywhere. Okay, because of high pressure and cyclic loading, so it can have uh, uh, the oil leakage in any part of this, or at any end of this hydraulic circuit. So in that case, the amount of oil which is lost in leakage needs to be replenished, means it to be replaced by the same amount of oil, so that the amount of oil that is required to run and to do the required amount of work is there in the circuit. So to cover that one, if it's very small quantity, that can be taken from here, but if it is some quantity that is large, then this replenishing pump is turned on. Okay, of course with the help of an electric motor, and then this pump takes the required amount of oil that is lost and that is less in this circuit, would just push that amount of oil through the filter and goes here. Now when it comes here, now we see what is the direction of the flow of hydraulic oil. If it is like this, okay, and the oil is less, okay, in that case it will come here, but it will not go from here, because now this is the high pressure side. Okay, it's a high pressure side, and this is the low pressure side. Okay, so in that case, when it comes here, because the high pressure side, it is being pushed against the seat, okay, or against the poppet or opening, so it will not open from here. So in that case, this oil, which is now the replenishing oil, or the to cover the oil, which is the lost oil, okay, to uh, to satisfy the lost oil quantity, it will go from here and push this one, because this is low pressure side. It will push this one and goes freely and enters into the circuit. And then this required amount of oil that needs to be replaced, or that needs to be just added to the circuit, would be added through this, if the oil is moving in this direction. If the oil is moving the opposite direction, in that case, the lost oil and covering up the lost quantity of the oil would be sent by this replenishing pump again here. Now, since this is the high pressure side, it will not open because the oil is just pressing this one against its seat, so it will not open. So the oil will come here, push this one because it's low pressure side, come here and then join the mainstream oil and continue working and flowing in the main pipeline, actually covering the lost or leaked oil. So that's how it works. So this is your replenishing pump that is just turned on if you see the oil quantity of the oil flow is reducing. So just you add more oil from here so that the oil, the required amount of oil remains in the circuit. Okay, so this is the example of the full hydraulic system, which is called hydraulic transmission system. So you say the hydrostatic transmission, the hydrostatic transmission system. So this tractor is a very good example of this complete hydrostatic transmission system. It says track type, tractor application. So two hydrostatic transmissions are there. So it means that there are two hydraulic systems in this. So one hydraulic system is controlling this, this barrier or this thing that goes up and down, move forward or backward, and other hydraulic system would be taking care of this one, which is the belt, the metal belt, which runs the whole tractor. So two variable displacement piston pumps are there. Each pump delivers 66.7 liters per minute at speed of 2,400 RPM and pressure 6,900 kilopascal. Pressure relief valve is set at a pressure of 17,200 kilopascal. Two piston motors. Okay, two piston motors. Okay, so the piston motors are used which run with either of why piston motor, because it is see the motion is linear. Okay, in that case when the oil comes here, okay, so this hydraulic cylinder, or you can just use some sort of piston motors over here as well. So, or maybe the piston motors are here and it is the hydraulic cylinder here. So hydraulic cylinder here, piston motors here. So two piston motor, one here and one the other side, which run with either of the two different volumetric displacement controlled by the operator to provide two speed ranges. Then with a single joystick, the operator can control speed, machine direction, and steering. The machine direction is how, if you apply the oil to come here, this will turn with the help of this piston motor, and the other will not turn. So it means it will allow this tractor or this earth mover to go in the other direction, to turn. Okay, and if he does the other way around, so that will stop, and the other will start working, and it will turn to the other side. That's how it works. So it means this is a very good and compact and complete application of the hydrostatic transmission system. It has two hydrostatic transmission systems that we have seen and we have learned. Now we have this situation analysis of hydraulic system with friction losses considered. So when we have the friction losses considered, so far we haven't talked about the friction losses unless we accept that we studied that the friction losses in the pipes and the fittings and vents in chapter number, I believe, chapter number 4. But after that, we didn't talk about that. We are going to combine those friction losses plus all these valve formulas and motor formulas and pump formulas to have the complete problem generated and solved for this whole system. So let's see the system. A hydraulic motor is there, but it is one single direction. So either like this or like that. Okay, so the direction is given, so it will be turning like this. So filter, tank, variable displacement, single direction, one direction hydraulic pump, which is run by the electric motor. So the pump would push the hydraulic oil into the pipeline with the pressure given here, and then this is the check valve. Now this check valve would easily allow and freely allow the oil to flow through it. Okay, it comes here. Now it has two branches. One is this one, and the other one is this. Again, this one is closed because the pressure setting is not reached. So it will go here, show the pressure after this because there's a pressure drop. You will see the pressure here. So P1 will be more than P2 and will come here and run the hydraulic motor. And of course, whatever you need to do through the hydraulic motor, you'll get it done. So once done, the oil will flow again to the circuit at low pressure and comes down to the to the tank. Okay, so this is a very typical example of an open circuit. Okay, and therefore this is your pressure relief valve. As soon as the pressure is high because of some restriction or some blockage, so it will just open and drain the oil in such a way that the pressure is maintained uh, inside the whole circuit. It will not shoot. Now, what is this? These are the nominal pipe sizes which are available in the market, of course, in inches. Okay, pipe outside diameter in inches, and schedule for, or maybe it's in outside diameter. Yeah, so outside diameter, I think it would be in inches, not in centimeters. I don't think so. That's just in centimeters. Schedule 40, schedule 80, and schedule 160. Okay, so these are the standard names or the numbers for those pipe inside diameters and pipe outside diameters. So it means now if you have a particular nominal size of 1/8 inch, this is your pipe outside diameter. I'll make sure that this is a centimeter or it's an inch. Okay, so you'll have for this particular outside diameter, for schedule 40 here, this inner diameter. So you can see just subtract, it will give you, and divide by 2 will give you the thickness of the pipe. And also schedule 80, again subtracting and divide by 2 will give you the thickness of the pipe. That's how the standard dimensions of the pipes, the outside diameter and the inside diameter, based on the or the required schedule number, you can get the pipe which is available in the market. Now let's see the problem. Now this is the problem that is a complete problem that include all the formulas of pumps, most of the formulas of pumps, the formulas of the motor, the friction losses, and all these will be combined together to have a complete problem of including all those equations and knowledge that we have learned so far. So before we read the statement, let's see the circuit first. Okay, the circuit is, okay, the pump is running with the help of a motor. I think this is the same circuit that we just saw. The same thing is happening. There are two pressures. One pressure is here, another pressure is at this point. So we take this pressure gauge as 0.1 and this pressure gauge 2 as zero point 0.2. Okay, and there is, of course, the pressure relief valve as well in between, and hydraulic motor is there. So let's try to read and see what the problem is and what is required. Now please pay attention, guys. The system shown in figure 9 dash, so this 9-26 contains a pump. Yes, it contains a pump. It's a variable displacement pump and a single one directional variable displacement hydraulic pump. Contains a pump delivering high pressure oil. Yes, of course, we know that. To a hydraulic motor, yes, of course, it has to supply a high pressure oil, which drives an external load, of course, via a rotating shaft. Yes, it is doing the work. The following data are given. Now let's see the data. The data for the pump is the mechanical efficiency of the pump is given, the volumetric efficiency of the pump is given, the volumetric displacement of the pump is given. Again, it is 10 inch cube per revolution. But don't worry. By the way, all these numbers which are in the English units have been converted into SI units. Okay, so don't worry. I have converted all those, and the solution, when you are going to see in the next slide, you will see all the values and all the parameters are in SI units. Okay, don't worry about that. So the RPM of the pump is given, which is 1000 RPM, and the inlet pressure, which is of course the suction pressure, is given as minus 4 psi, which is 4 psi less than the atmospheric pressure. Okay. Now hydraulic motor mechanical efficiency is given, volumetric displacement, inlet pressure P2, required to drive the load. So inlet pressure is given, and the motor discharge pressure, the pressure which is generated at the other end, discharge end of the motor, is given. Okay, so we need to see what is the net pressure which it takes to do some external work. Pump discharge pipeline. 1 inch, okay, 1 inch, schedule 40, 50 feet long. So length of the pipeline is given from point 1 to point 2. So as I mentioned, I take this pressure gauge 1 as 0.1 and pressure gauge 2 as 0.2. So between these 2 points, the length is given, the diameter is given, and so on. Okay. Now fittings. For some fittings, there are some fittings. One is the two 90-degree elbows in which the K factor is given as 0.75 for each elbow. Okay, so for each elbow means if you are going to do it to find the equivalent length, so you have to multiply by 2 because there are two 90-degree elbows. So this is what you have to do. And then one more thing, which is one check valve, which is K is equal to 4. Is equal to 4. So we have one check valve and two 90-degree elbows. What else? Viscosity file is given. Centi-stroke we can convert it very easily to meter square per second as a kinetic viscosity. Specific gravity of oil is 0.9. If the hydraulic motor is 20 feet above the pump, the hydraulic motor is 20 feet above the hydraulic pump, determine the number one pump flow rate. So I need to find the actual pump flow rate which it delivers to the pipeline. Number one. Okay. Number two, pump discharge pressure. So the discharge pressure, which is P1, we need to find this one too. Input horsepower required to drive the pump. So input power is required. So again, we are not going to find horsepower, but we're going to find the inlet or the input power required to run the pump in kilowatt or watt. Motor speed, of course, we need to find the motor speed RPM. Then motor output horsepower means the what power it delivers to the load. Again, we are not going to find in horsepower, but we are going to find in watts or kilowatts. Motor output torque. So actual torque at the output, okay, at the outlet. So what torque is produced? Is produced at the delivery end or discharge. And last, the overall efficiency of the whole system. This is very interesting. When you come to the last G part, you see if you want to find the overall efficiency of the entire system. Before we know that the overall efficiency of pump, overall efficiency of motor, but what about the overall efficiency of the entire system? And we're going to see that one at the end. Okay, so this we're going to see all those. So we need to find all these based on the data given to us of all the things. Now, since we have these fittings, elbows, and the check valves, so it means that will be having, of course, check valve. We can see the check valve. So it means all these would be included towards the friction effect, the friction and the pressure drop because of the friction in the whole circuit. So let's go to the solution. Here we go. 9-6 or 9.6, the pump values or the pump data is given. This is just a bit. And see here, as I mentioned, that I have converted this volumetric displacement into meter cube per revolution. Okay, so don't worry, you will have all the data in SI units. So you just can use the SI unit data as it is. RPM, of course, will remain the same. It will be RPS, revolutions per second, and then radians per second. I convert it now because whatever I need, I can just take the value from here. Then inlet pressure is again minus 27. Before it was minus 4 psi. If you convert psi into kilopascal, it will be minus 27.579 is the suction pressure. For hydraulic motor, we have mechanical efficiency, volumetric. Again, I converted into meter cube per revolution for the volumetric displacement of the pump of the motor. Then the inlet pressure P2 to drive the, again I converted from psi to kilopascal, and then motor discharge pressure, which is at the outlet of the hydraulic motor, I also converted into kilopascal in SI units. Once done, now we have for the discharge pipeline, we have the pipe diameter 1 inch, schedule 40, LP length of the pipe or length of the pipe is 15.2. Again, I converted from feet to meters. Then fittings, we have 290-degree elbows in which K value is given. The K factor is given 0.75 for each elbow. Okay, remember the each elbow. So it means I have to multiply by 2 when I get the when I find the equivalent length for these fittings. Then one check valve, which is K is equal to 4. For oil, kinematic viscosity in centi-stroke and specific gravity is given as 0.9. So hydraulic motor elevation is 6.096 meter, which is of course converted from feet to meter, and which is of course equal to Z2 minus Z1. So we need to find the actual pump flow rate, the out discharge pressure, P1, power of the hydraulic pump, which is provided to the pump to run, and then the RPM or the angular velocity of the hydraulic motor power of the hydraulic motor that is produced by the hydraulic motor, and then the torque, actual torque produced by the hydraulic motor, and last, the overall efficiency of the entire system, not motor, not pump, but the entire system. We'll see how we can find it. Okay, let's start with the solution. The solution, okay, everything is good. So the solution will start by taking the pump and finding the theoretical pump flow rate. Okay, it is VDN. VD is the volumetric displacement, which is given in meter cube per revolution, and N is given in RPM, but I will use in RPS because in this way, if I multiply RPS with the meter cube per revolution, it will give me meter cube per second, which is an SI unit. Okay, so in that case, I will not put radians per second because there is no benefit of taking radians per second, but the revolutions per second would be beneficial because it is 0.00016 per meter cube per revolution, and that will be revolution here you meter cube per revolution for this one, and N is revolution per second, revolution cancels, and meter cube per second will be the SI unit for the volumetric flow rate of the pump, and it's theoretical. So since we have theoretical pump flow rate, we have actual pump flow rate already. We can find actual because we have volumetric efficiency here. So we know that volumetric efficiency of the pump, of the hydraulic pump, is Q actual over Q theoretical. So actual flow rate it produces, which is of course less than theoretical flow rate it should produce. So in that case, we get the actual flow rate of the pump from here. So part A is done. So let's go for part B, which talks about and which asks the pressure at the outlet of the hydraulic pump. So in that case, for that we have to use the Bernoulli's theorem or the energy equation so that we can find the P1 pressure at this point. So for that, for P1, determine the frictional pressure loss. We have to find this one, P1 minus P2 in the pump discharge line. Energy equation between 1 and 2 means the stations 1 and 2. Okay, will do. So we apply the energy equation in which we have the pump loss, pump head, the motor head, and the head loss, and we have the elevation, the pressure head, and the velocity. Okay, everything is there. So since between these two pressure lines and between pressure gauge 1 and pressure gauge 2, there is no pump, there is no hydraulic motor, so it means we can ignore and cancel those because there is nothing like that here. So the HM will be 0. There is no motor. The motor head will go away. A pump head will go away. And also since the velocity is supposed to be continuous, so it means V1 will be equal to V2. So this and Z2 minus Z1 will be equal to 6.096, which is given in the problem. So simplify for a lot this equation because many terms will cancel and you will left with a very simple equation and then we're going to solve. But for that we have to find the velocity and the kinematic viscosity and so on, and we find the what is it, Reynolds number and then friction factor, and then from there you can find the equivalent length for the fittings, and then you can add those to get the head loss, which is HL. Of course, this head loss will remain there. So let's find the velocity. Of course, Q actual we just found. So Q actual over area, which is the area of cross section of the pipeline, which is the inside diameter of the sorry, based on the inside diameter of the pipe. The area is found, which is pi by 4. This is the inside diameter. So if you just go back, you will see this is being calculated, which is I think it's somewhere here. The diameter is calculated. The diameter is here. So 1 inch. So when you convert this into into meters, so this is what you'll get: 0.0264 6416 whole square. Okay. So this is your diameter, and you multiply by pi over 4 to get the cross-section area. So you divide, and you'll get this this number. Oh, here is there. So here you go. Okay, so it is now for sorry for the pipe diameter. So we'll see 1 inch schedule 40, and then we get the value from there. So it means we get back to the table. So we have to go to 1 inch, right? 1 inch nominal size, which is this one, and we 40. Okay, so this is so it means it is in inches. If it is in inches, then you convert it into meters. So you'll get something like this number. Okay, that is inches. Now confirmed. Get the pipe from there in meters, and we put it there to get the flow velocity of the hydraulic oil inside the pipelines. Then we get the idea of the parameter which is equal to 125 centi-stoke. So if you want to convert the centi-stoke into meter square per second, just divide by times per 6, it will convert into meter square per second. Here you go. The value is given. So this is the value that you will find for the viscosity. Why we are getting these parameters? Because we want to find the Reynolds number, and for Reynolds number we need the velocity, we need the diameter, we have it, and we need the kinematic viscosity or dynamic viscosity. So here, since we have the kinematic viscosity or the kinematic viscosity, and now we're going to use the Reynolds number formula Ed over nu for B, that we found V, which is equal to 4.59. D, we know that, and then this is your nu, the kinematic viscosity. You get Nr is equal to 970, which is laminar, of course, which makes our life easy because the very simple formula is a 64 over Reynolds number. We put the value, we get the friction factor, which is very, very small. So now we're going to get the equivalent length and then find the head loss. So F, which is the friction factor, equivalent length, total. Total why? Because equivalent means that you add uh, the length of the pipe to the equivalent length of the what do you say, of the check valve and of these two fittings. So that would be just added to, all in this one. The diameter D is the internal diameter of the pipe. Again, V square is the velocity, and 2G, you know that. So let's see and get the equivalent length first, and then put the value here. So the 15.24 is the total length of the pipe. 2 into kd over f is the formula. This is standard formula that you should know. K is given in the problem, which is I think 0.75. 2, see, I said that you have to multiply by 2 because you have two of these fittings. So multiply by 2. So this is the formula for 1, and then multiply by 2 will give you the K, the value of the equivalent length that can be added. So K is 0.75 given, D is for the internal diameter, and F is the that you just found, which is over here for the value. Okay, so K is given 4, diameter remains the same, and F, as of course, is 0.06 the friction factor for the entire circuit. So when you simplify, you get the LE total, means total equivalent length equals 17.44 meters. So this is the total equivalent length because of the pipes, because of the fittings, or because of the valves. Once done, so now we can put this equivalent length here to get the head loss. F is, of course, we know the friction factor 0.066. The equivalent length, I put it here. D, again the diameter, we know that. V square, we found the V, and 2G, we know that. So we simplify to get the head loss, which is 46.79 meter. Okay, we get HL. But again, HL would be used only in the energy equation to get P2. Now, equation 1, so equation A would become, after applying substituting all those parameters, so solve for P1 minus P2 over gamma. So gamma is, of course, uh, the specific volume, so that will be found. Z1, Z2, of course, you move this Z1 to the other side. Z2 minus Z1 is 6 point something, is 6.096. HL you just found. P1 minus P2 over gamma, so gamma is taken common, so P1 minus P2 is equal to this. So put the value of Z2 minus Z1 and HL as you just calculated, and this is the expression you have. But before that, we have to find gamma, the specific weight of the oil. So gamma of oil is, of course, gamma of oil over gamma of water. So gamma of oil would be equal to specific volume, specific volume. So that will be the specific gravity over the specific volume of water, which is 9810. And we know that how we find it. We get the weight and then we divide by the volume to get the specific volume of water, which is a standard one to be taken as reference. We multiply, we get the specific volume of the of the oil, gamma oil. So this gamma oil put here, multiply, you'll get P1 minus P2. This is the number that is P1 minus P2. But again, we are going to find P1. We need to find P1, which is the discharge pressure developed or established or provided by the hydraulic pump. So in that case, I need to move P2 to the other side. It will become P2. Now what is P2? P2 is 3447.38, which is given in the as the given value which is here. So inlet pressure. So P2 is the pressure which is provided here at the inlet. So this is what you're looking for. Okay. So P1 minus P2, and P2 is the inlet pressure which is given already as 3447.38. Again, this is converted into kilopascal. It was given as psi as 500 psi. Okay, so we put this one here, and here we go, and we get P1. So once P1 is calculated, this is what was asked. So this part is done. Let's go to the next part. Next part says the power provided or given to the hydraulic pump. So I know that we can very easily find the overall efficiency of the hydraulic pump as this multiplication or the product of mechanical efficiency and the volumetric efficiency. So put the values and you get the overall efficiency of the hydraulic pump. So once you get it, now we have the other formula of the overall efficiency, which is the hydraulic power. I will say the hydraulic power delivered by the pump, and this is the mechanical power. I think it's a mistake. Mechanical power, actual mechanical power delivered to the pump. So mechanical power, which is of course coming to the top to the pump. So it means that if I want to find the power delivered to pump, so this is unknown, and I can put this one, the expression for this one, this I just found, and find this value, the hydraulic power delivered to the pump. So you move this to the side and eta naught in the denominator, and hydraulic power there is PQ, P which is of course P at the exit, and actual flow rate, okay, for the pump and for the flow rate. So this is over eta naught, and so this P1 total, which is the power, the pressure provided by the pump, is 3914. This is what we, here we go. So we have this exhaust or the discharge pressure developed or provided by the hydraulic pump. So this we have it. So we put P, and Q actual is the what do you say, the actual volume flow rate, which actually is already calculated, which is here. Here you go. So here you go. We have already calculated the actual volume flow rate. So we have this one. We have the other parameters, which is here, yeah, from this one. Yeah, here. So we put the values. Here you go. We put the values over eta naught we just found. You simplify, you'll get the power delivered to the pump, which is 11.46 kilowatt. So this is the total power delivered to the pump to produce the required amount of pressure and so on. So next is I want to find the, yes, any question?
Doctor, from when we get this 27.579 after the B of the pump, B inlet?
P inlet? Right now we are not using this one. Okay, if you're talking about this one, this one. This one will be used if I want to find the total amount of force produced at the motor. Okay, in that case, if you remember, we used this one when we wanted to find the total amount of force or total amount of pressure, and from that pressure we can find the force. So we are not actually calculating here in this problem the total amount of force that is required to be produced by the pump in order to compensate or to cover or to to balance all the resisting pressure drops, so that the required amount of force is produced or is provided at the motor side. So that's why
But
right now we're not going
it's
to
written,
include, because this is not being used right now. Yes.
it's written in the solution. You can see.
What? What? Where is
Okay.
it?
Yes,
Where?
here
No, yeah,
3914.
yeah. Oh, no, no, no. Oh, okay, okay, okay. I get your point. I get your point. No, no, no. This had to be added. This had to be again the same thing, because it's a suction pressure. Yes, you're right. I have to mention this. It needs to be added. It needs to be added to this. So you have to add this, because why? Because it is starting from a pressure which is lower than that to a pressure which is at P1. So you need to add this. You need to cover this this pressure to compensate for the total pressure which is provided at the outlet. Okay, so this here, because the pressure is now what is going on. This pressure is starting from zero pressure gauge to this amount. Okay, but what about this pressure? So the pump has to start from the pressure which is below it to this. So it means you have to add this one. Okay, is it clear?
Okay, clear.
Yeah, so you have to add. So this is what we did earlier. So we're going to do the same here as well. So we add this here to start the to let the pump start from a pressure which is lower than atmospheric and reach at this pressure value, and then multiply by Q and you get the power. Okay, so let's continue. So we have now D, which is I want to find the what is it, the uh, the RPM or the volumetric, so the angular velocity of the motor and motor. So now in order to find this one, we know that when if we ignore those losses, okay, so in that case we say that the Q actual pump which is delivered by the pump is equal to the Q actual the actual volume flow rate received by the hydraulic motor. Okay, so this is something which is not correct, but this will simplify the calculation. If we have not a very accurate, calculation required, so in that case we can take this one. Of course, there's losses which we ignore between these two, but we take this one. So in that case, we want to just find the theoretical volume flow rate of motor, and then you can just use this to find the other one. So in that case, if you want to find this one, we have the volumetric efficiency of motor given. We have the actual motor, which is again coming from the discharge volume flow rate from the hydraulic pump. You see here actual motor, so it is the value which is which was calculated over here, uh, which is here, which is here, here you go. So this value is put here, here you go, and you get the theoretical volume flow rate. Why we need it? Because when we have this one, we can just use the volumetric displacement of the motor, and you can find the angular velocity. Because now we have the theoretical volume flow rate, we just divide by this, and then we get it. Now let's see the units. The units are very important. The units need to be understood very clearly, because if you make wrong units, then it will be a big problem. Now we know that we have this Q theoretical in meter cube per second. And this Vd is meter cube per revolution. Meter cube per revolution. So in that meter cube would cancel, you'll be having revolutions per second. So the number that you'll get will be revolutions per second. It will not be RPM, it will be RPS. Okay, so here you go. And then you multiply by 60, of course, to get RPM, and then multiply this RPS by the 2 pi to get the radians per second. Okay, now we have got all the three values of the angular velocity of the hydraulic motor. Next one is the power produced by the hydraulic motor. Okay, so in that case, we need to find the motor input horsepower, okay, which is in watts or kilowatts, and then I'm going to find the power produced by the hydraulic motor. So we have now PQ is the hydraulic power that is produced, PQ. Okay, P is the pressure, and Q is actually the volume flow rate. Now here, please pay attention, guys. Here you see the discharge pressure. The discharge pressure is subtracted, because what is happening? This is the total pressure coming entering to the hydraulic motor, and this is the pressure which is still there, which is not utilized and which is not used by the hydraulic motor. So this is the discharge pressure. This is the inlet pressure. So it means that the net pressure would be the pressure would be the total energy which is or the total power provided to the hydraulic motor, because this is not used. So this net needs to be separated. So we need to know the net uh, the net pressure that would be able to produce the required input power. So this is subtracted. This is the one which is the discharge pressure that is at the discharge side of the hydraulic motor. So we subtract because this is not being utilized, and this is the one that enters, and the balance would be, or the difference would be the one that would be used as the power input. And Q actual motor, we know that, which is coming from the actual pump flow rate, and then we multiply to get the power which is received input to the hydraulic motor. So this is the power received by the hydraulic motor, which is now available to do work by the hydraulic motor. Now, once it's done, now we know the overall efficiency of the hydraulic motor, which is given, which is of course the product of volumetric efficiency and the mechanical efficiency of motor. So multiply those, so it means this is known. Okay, so this is the value that you have it. Now you have this one. I need to know the motor output power. Okay, so I have the motor input power, which is in the form of hydraulic power, and this is the motor output power, which is in the form of mechanical power in the form of the torque, and this is the overall efficiency. So multiply this one, you'll get the motor output power as equal to 7.1 kilowatt. So you can see how the values are changing. So this is the power provided to the motor, and this is the power it produced from the power which it received. So it means the balance or the difference would be the losses that would be used to compensate for friction, for the the viscous forces, and those are resistances that would be taken care of with the help of this difference in the power received by the hydraulic motor and the power produced by the hydraulic motor. Now the next one is motor output torque. Okay, the motor output torque, which is the Tn, the T actual power torque, and the RPM, which is the angular velocity. So since we need the torque, so we just divide this by n, and power produced by the motor is 7100, which is here. Okay, and divided by the RPM, which is 108. Now this comes from where you have to is the motor angular velocity in radians per second. Now here very important, and you just make sure that you put the right unit of the angular velocity. Before we used the revolutions per second or revolutions per minute, but here we are using radians per second. Okay, as I told you, if you are going to use these, if you are going to use now this eta naught, and instead of using this to find this this Tn over Pq, in that case you are going to use the n as radians per second. Always whenever the efficiency is involved, you're going to always use the radians per second. So that's why you're going to use radians per second here instead of revolutions per second or revolutions per minute. When you simplify, you'll see it will come out to be Newton meter, which is the unit for the torque. Actual torque of the motor is 65.4 per Newton meter. Okay. Now this radian, it will not be visible, and it will not be considered because if you remember, I mentioned the radians is considered as a dimensionless unit. So it means it's not considered as a unit at all. Okay, that's why you see it remains there, but you're not going to write. Okay. This Newton meter is the torque of the hydraulic motor. Now the last thing, which is very interesting, and this is what I want your attention, is I want to find the overall efficiency of the entire system, not the entire, not the equipment like hydraulic pump or hydraulic motor, but the entire system. So in that case, if you see the statement, you'll see that motor output power, which is the power produced by the hydraulic motor, and power input to the pump. So pump input power, and pump input power was given as was calculated as this one. So 11.46 kilowatt of power was given to the pump, and at the end, the power that it received for use of work was 7.1 kilowatt. You see the difference. So 11.46 and 7.1. So we want to find the efficiency 7.1, which is but of course I don't like this one, but it's still there. But I will just take the whole thing as 7100, which is mentioned here. So 7100 over 1146, it will give me an overall efficiency of the entire system as 61.95%. So that's how, if something like that comes in the exam, to find the overall efficiency of the entire system. So it will be the final output and the initial input. The initial input is the power, the mechanical power produced by the mechanical power provided to the hydraulic pump, and the mechanical power produced by the hydraulic motor. So both will be mechanical powers. Okay, mechanical power provided to the pump with the help of torque from the electric motor, and the mechanical power produced by the electric motor in the form of torque. And that's how you find the overall efficiency of the entire system. So anything which you want to ask, then we'll go to the next question. Okay, let's go to the next question. It is now a problem. This example, I selected this one because it is a very comprehensive example which covers all the things. Okay. Now we're going to talk about, so you see, talks about it has taken care of all these efficiencies and even the losses as well, which we just calculated over here. So all the losses and friction and all these things are taken care of. So this is a very comprehensive problem. So just be ready for this type of problem if if I give you something like that, or maybe some part of it. So let's see this problem. This is a unsolved problem at the end of the book, but I added and I attached I included the solution of this whole system. Okay, of this whole problem. So we have to read the problem, and then we are going to see the circuit, and then we see how we can get the results. So see the problem. Let's read it. Solve the problem of example 9-5. So he's referring to the example 9-5 to solve whatever is asked in example 9-5, but we have to just add few parameters here in this problem and then solve this problem with those new parameters added to this problem, where the pressure drop equals 300 kilopascal in the pipeline outlet, from pump outlet to the blank end of the cylinder. So from here, blank side. So it means we just go here. So from here to here, the total pressure drop is given as 300 kilopascal. Okay. So whatever pressure is developed here, you will get a value of pressure 300 kilopascal less than what it produced. It's produced at the pump outlet on the pump discharge. Also, the pressure drop equals 200 kilopascal in the oil return pipeline from the rod end of the cylinder to the reservoir or the tank. So from rod end, from here, it can go from here, it will go from here until the tank. The total pressure drop for this line is as 200 kilopascal. So it means that if you are having this tank open to the atmosphere, so at this particular end, the pressure of the oil is uh, uh, 0 pascal gauge. Okay, 0 pascal gauge. So it means that if this is 0 pascal gauge, there should be a pressure of at the north side, a pressure of 200 kilopascal, so that this is dropped to zero pascal gauge. So we will talk about that and we'll see. So these are the two pressure drops given at the blank side and the rod side of the heterocylinder of this circuit. Now let's see the problem of example 9-5 for the meter out. Okay, meter out. Why meter out? As I mentioned, meter out is always in the rod side. So it means when the oil goes out of the rod side, the flow control valve, which is in fact here in this case a needle valve, is placed here at this rod side of the hardware center, not at the blank side. Which uses a suspended load. Now the load needs to be suspended, means the load need not to be lowered, not raised. Okay, so it needs to be maintained and suspended at this location. Okay, this is important. Uh, Suspended determine pressure on each pressure gauge. So we have three pressure gauges, 1, 2, and 3. So all three pressure gauges, we need to find the pressures at these three pressure gauges. Okay, one at the blank end, one at the rod end, and one after the flow control valve. Determine the and during the constant speed extension of the cylinder for no load, when there is no load. So there is no load, just the piston and the rod are there. Just piston and rod are there. So there is no load. What will be the pressure at V1? What will be the pressure at P2? What will be the pressure at P3? Number two, now you put a load of 20,000 Newton over here attached with the rod. But again, as I mentioned, the load needs to be suspended. It should remain suspended. So it means the piston should not go down. Okay, so in that case, we need to see what pressure will be developed so that the piston doesn't go down. Okay, so the central piston and rod diameters are given, and the pressure relief valve setting is given as 10 megapascal, which is here. Okay, pressure relief valve, which is 10 megapascal. So this is 10 megapascal, and it just goes to the P1 and so on. Let's go to the solution. The solution says that delta P is delta P. So delta P from the pump to the blank end of the hydraulic cylinder is 300 kilopascal, which is given. The pressure drop is given as 300 kilopascal, which is of course 300 liters per 3 Pascal. And for the return delta P, the pressure drop is 200 kilopascal, which is 200 liters per 3 Pascal. We need to find P1, we need to find P2, we need to find P3 for no load at the rod and 20,000 Newton load attached to the rod of the hydraulic cylinder. Okay, what else is given? The piston diameter is given, the rod diameter is given, the pressure relief valve is given, which is the pressure rating, the pressure setting of this is 10 megapascal, which is 10 to the 6 Pascal. So the solution for A part, when there is no load at the rod end, we will find first of all the pressure P1 at this at this pressure gauge. Okay, so now we know that the pressure, whatever pressure starts here, okay, the drop will be 300 kilopascal. Okay, so that pressure, which is the pressure relief valve, which is 10 megapascal, because you see it's the same pressure which is letting the oil set at this 10 megapascal, and the same pressure would go at the maximum. So it means the pressure drop from this pressure would be 300 kilopascal. So you just subtract the 300 kilopascal from the pressure relief valve pressure. So 10 to the 6 millimeter. So this will be the pressure of P1 at this pressure gauge 1. Okay. Now this pressure is going into the hydraulic center. Okay, the blank end. So it means we can find very easily the force. The force will be, of course, the pressure into the area. Here we go. The pressure into the area. Pressure is 9.7 times per 6, 9.7 megapascal into area, which is 542.0.05. The diameter of the piston is given. So we get the force which will enter the blank side of the blank end of the hydraulic cylinder. So we know that now we can apply here the Newton's second law of motion, and we balance the forces, because as I mentioned that the load needs to be suspended. So it means the forces should be balanced so that it doesn't go down, it doesn't go up. Okay, so in that case, whatever force is applied at this end should be equal to the force applied at the opposite end, so that both are balanced and nothing would happen. Okay, so in that case, we have to equate both forces on both ends, and then we can find from there P2. Here we go. Force at the blank end should be equal to the force at the rod end. Okay, that's how we can get this piston not moving up or down. So this force at the blank end we just found 19,000 Newton, and force at the rod end is what? The P2 into AR minus AP, AP minus AR. See, P2 into the area of the piston minus area of the rod. Okay, so P2 is, of course, we don't know P2, but we know the diameter of the piston and the diameter of the rod. We put the values and get the difference of the areas, and then we get from here the pressure P2, which is equal to 12.9 megapascal, which would be generated at the rod end of the hydraulic cylinder when there is no load. Okay, remember that it's just because of this hose setup. This will be the pressure developed at the rod side. What about P3? P3 is simple. Well, P3 is just next to the tank, so it will be zero gauge pressure. Here we go. Done. So part is done. Now we suspend 20,000 Newton of force or the load at the with the rod. Okay, when we put this 20,000 Newton of load with the rod, we are going to find all together these three pressures P1, P2, and P3. Now, what about P1? P1 will not change because this load is applied here, and this is providing that same pressure, whatever is provided by the pump, which is of course 10 megapascal minus 300 kilopascal. It will not change. Okay, so it means that there should be some extra force developed at this end so that this the piston doesn't go down. So that's why P1 will remain the same as it is, because there is nothing extra provided from the pump. The pump is running as usual. But when you apply the Newton's second law of motion with this load, so you see two forces are pointing downwards, and one force is pointing upward. So this force, which is at the blank end, is pointing downwards because of this pressure provided by the pump, and the load is also pointing downwards. So these two would be added minus this force, which is in the opposite direction, to balance it. Okay, so again, P1 into AP plus this load, which is 20,000 Newton, minus P2 into AP minus AR. Here you go. P1 plus the load minus, and you can move this, the whole force on the other side, because there is no acceleration. MA will be zero because acceleration is zero, because nothing is moving. So we move this minus P2 into A2, AP minus AR to the other side. So now you want to find P2. Of course, everything is known. You get P2, which comes to be 26.5 megapascal. And for P3, since we know that in the third part, now what you'll see, in the first part there was no load. Okay, so it was just moving on. But now once the load is there, so the extra pressure is applied. So that extra pressure of 200 kilopascal will be applied, which is mentioned here. So that 200 kilopascal would appear here because it will also sense this pressure. But of course, this pressure would be dropped to zero when the oil, if it goes at this. So at this end, the pressure will become zero pascal gauge, but at this end, it will be the pressure, which is 200 kilopascal. So that will be the P3, which is at this end. So you can see the difference. When there is no load, it will be just at the atmosphere. But then when the load comes, this pressure is felt by the P3, because of course you apply a force, and some force would be transferred, and that would also be felt at this point, at this pressure gauge P3. That will get the 200 kilopascal. So this 200 kilopascal is coming from the data which is given to us is over here. The pressure drop equals to 200 kilopascal in the oil return pipeline from the rod end of the cylinder to the reservoir. But this will not appear when there is no load, because there is nothing felt, and this amount of force will balance this force, and there will be nothing here. But as soon as the extra load is there, this pressure and this force will be felt here. This will give us the extra pressure of 200 kilopascal, which is mentioned as a pressure drop from the rod end to return at the tank. So it means this pressure will be felt here as P3, which is 200 kilopascal. So that's how we do this problem. So that completes the course. These are the two problems that I want to do, especially this first one, the example. Even though it's an example, but it is a comprehensive problem that we've seen many things that we learned and we implemented. And here this one also is important, because this will take care of these pressure drops and how you're going to apply these formulas and these Newton's law of second law of motion, so that you can get the force balance and get the results at the end. Okay, that finishes the course. Inshallah, Alhamdulillah, we finished all those 9 chapters. And the problem that I wanted to mention, almost I think all the problems we have discussed in the class or now in this online class. So that completes the chapter. Now, as I mentioned about the material, it will be coming from chapter number 5, then 6, 7, 8, and 9. So it means just 5 chapters. So first 4 chapters will not come in the exam. Okay, so that would just relieve you from this course, even though this course is simple and very easy, because we have very simple and small formulas, nothing big or long, or no derivation, no differentiation, no integration, nothing. So that makes this course very easy and practical. And we have learned many things about the types of the pumps, types of the motors, the overall fluid power system, and the benefits of those and the utilization of those. So now you can just, now since we have done the course, you'll see that if you just go and see different machines and different mechanisms, you'll see the hydraulic power just working almost everywhere. You'll see that. You just pay attention, you see almost all the things are using this fluid power system in their mechanisms. Okay. So anything you want to ask, you can ask right now. Go ahead.
Doctor, I have a question about the final. The material before mid is with us.
Say it again, please.
In the final, the material before the mid is with us or not?
No, the material before the midterm is not in the final exam. So the final exam is, please note down, The final exam is from chapter number 5 up to chapter number 9. Okay, please note down chapter 5 to 9. So 5, 6, 7, 8, 9. Okay, so these 5 chapters: chapter 5, chapter 6, chapter 7, chapter 8, and chapter 9. So 9 chapters. Okay, so 5 to 9.
It will be 5 question or
I don't think so. I don't think so. 5% will be too much. Even though you see the problems are simple and small and short solutions, but like for example, this example 9-6 is a very huge problem. But of course, I just made sure that okay, the amount of the number of questions uh, that you can do very easily are put. Not very large number of questions or not very low number of questions. Okay. So the number of questions are very moderate.
okay. Thank you, Doctor, very much.
You're welcome. Any other question? Anyone wants to ask about the exam or anything else? Okay, so
Doctor,
question. So guys, yeah, go ahead.
there will be theory in final or
Yes, yes, yes. I always give theory, but again, as I mentioned, and I think you might have known by now from the midterm and the quizzes that I put theory as objective type questions. Okay, so I usually use 3 types of objective type questions. Number one is the, of course, the multiple choice, or fill in the blanks, or true false. So either of these types would come as objective to cover the theory. So also guys, I want to mention, as I mentioned yesterday, about especially the chapter number 9 chapter, that all these circuits, they are like more, I think more than 25 circuits that we studied, and we listened to the working of those circuits to do different jobs. You have to do all those circuits yourself, as I was doing in the class, that how you can see the hydraulic fluid flowing to do some particular job, and the particular function for that particular circuit. You have to do the same way. You just go with the oil, we go in the circuit and see how it works. Okay, you have to do all these yourself. Okay, and if you are stuck somewhere, read the description in the book that I, of course, is already with you, or otherwise if you don't even understand, just come to me. Still you have time. Tomorrow, day after tomorrow, maybe next week, come anytime and then ask me if you have any question, anything which you want to ask and clarify. I'll be happy to answer, inshallah. Okay. Okay, that's good. So inshallah, good luck, and I hope so far what I've seen, that so far your results are okay. I need to just grade your quiz and assignment, and I hope all of you would get very good grades. Like the average grade would be maybe B, or I think B. This is what I see the profile. You might have an average grade of B, which is very good. Okay, for this course. So inshallah, push yourself and get the most out of this 40% left in the final exam. Okay. Just few more things regarding the formulas. The formulas, which are, of course, we saw no difficult or long formula, but at least I put something at the end. So when you get the exam, in the exam paper, yeah, in the exam, so you'll just go at the back and you'll see all the formulas that you might be using. So please do, especially for a little bit longer formula, don't rely on your memory, but go at the back of the exam and you will see the required formulas that you might be using for, if you face that, okay, these are long and difficult formulas, so you'll find all those formulas at the back. So don't rely on the memory for those formulas. Go at the back and take from there and then use those. Okay. Okay,
Okay.
that's good. So that is, yeah, this is what I wanted to mention. If you have anything else, you can ask me right now. then that is closed. This will close this session. So see if you have any other question. Okay, if no question, then inshallah, good luck. And still, again, till the exam, I'm open for your any question. I'll be happy to answer and uh, work towards your better preparation in this course. Good luck, and inshallah, I'll see you maybe in some other course if someone has some course remaining. Inshallah, maybe in the coming semester, summer, or maybe after that. I'll see you over there, inshallah.
Thank you, Doctor, very much.
Okay, so inshallah, you're welcome. You're most welcome, and anytime I'll be there for your help, inshallah. Okay, assalamu alaikum.